Today I'm going to follow up my favorite video that I've ever made, and that video was about the Witt algebra. And in particular, we're going to construct the central extension of the Witt algebra by a one-dimensional abelian Lie algebra, and that is called the Virasoro algebra. The Virasoro algebra is maybe one of the most important algebras in mathematical physics today. But before we jump into that, we have a few things to do first. We'll recall what the Witt algebra is, and then we'll look at the basics of what a central extension of a Lie algebra is. Okay, so the Witt algebra is the Lie algebra of derivations of Laurent polynomials. So we went through all of these details in a previous video, but all of that ended with a basis for the Witt algebra given by these operators L sub n indexed by the integers. And in fact, L sub n took the form minus z to the n plus 1 times d by dz. So that's a differential operator or a derivation. So that puts it in this space right here. Furthermore, we calculated the commutation relations of these operators as follows. So the commutator of Lm with Ln, or the bracket of Lm with Ln, is m minus n times Lm plus n. Like I said, we're going to construct a central extension of the Witt algebra here, known as the Virasoro algebra. So I'm pretty excited for this video. Okay, so we first need to talk about what central extensions are. So let's suppose that we have an abelian Lie algebra. It's important that it's an abelian for this to be a central extension. Otherwise, it's just an extension. So we'll call our abelian Lie algebra A. But I'll use this MathFrak font, so it looks kind of funny, but that's kind of standard. So let's suppose A is an abelian Lie algebra, and we're going to work over the base field of C, although this could be done over finite fields, and the Witt algebra as well as the Virasoro algebra have been studied over finite fields. Okay, so we've got A, which is an abelian Lie algebra, and let's say G is a Lie algebra. So this is any Lie algebra, finite dimensional or infinite dimensional. And then here's the definition that we're making, which is the central extension. So we say G prime is the central extension of G by A if we have the following short exact sequence, which is also built out of two maps. So if we have, first of all, an injection, which goes from A to G prime. So I'll call that iota, and I'll notate that it's an injective Lie algebra homomorphism by this little hook. So that's the notation, the shorthand for that's an injection. Okay, furthermore, we have a surjection, so I'll call that pi, and it goes from G prime down to G. So you can notate that with this like double-headed arrow. So G prime down to G, such that we have the image of iota is equal to the kernel of pi. So I'll write that as follows. Image iota is equal to the kernel of pi. But that can be explained by the exactness of a short sequence. In other words, by a short exact sequence. And that short exact sequence is given from the trivial vector space into A. So we've got the map. That just includes 0 in as the 0 vector. And then we have our injection here that goes to G prime. Our surjection here that goes down to G. And then the map to 0 here. So how we read this, by exactness, we have the kernel at every step is equal to the image at the previous step. So here the kernel of pi must be equal to the image of iota. And then the kernel of iota is equal to the image of this map. But notice that the image of this map is just 0. That makes iota equal to an injective map. And then further over here, we have the kernel of this map to the trivial vector space is equal to the image of pi, but that kernel is everything, meaning that pi is onto or surjective, which is exactly what we need. Okay, so now we're kind of in a good place. Maybe I'll put a box around this and note that that goes hand in hand with the 2 boxes or the 3 boxes around these things right here. So this is a shorthand, kind of more modern way of writing that down. Another thing that we notice is by the first isomorphism theorem, we have G is isomorphic to G prime mod the kernel of pi. But since the kernel of pi is equal to the image of iota, this is equal to G prime mod the image of, so image of our injection iota. But notice that the image of iota is equal to A, or it's linearly isomorphic to A because that's an injective map. So that means we have a linear isomorphism between the following Lie algebras that are on the board. So what I mean by a linear isomorphism is that's an isomorphism as vector spaces, meaning we still need to endow the larger structure with the structure of a Lie algebra. Okay, so anyway, we've got G prime is isomorphic to G direct sum with A. Okay. So, like I said, we just need to sort out what the bracket is on G prime. So, in other words, we need the bracket, which is a bilinear map from G cross G to G prime, I should say. But a bilinear map from G prime cross G prime is the same thing as a linear map from the tensor product of those, if you want to like skip a step. Okay, so let's just reiterate what's happening here. We know what the bracket is on A. That's clear. It's trivial because this is an abelian Lie algebra. We know what the bracket is on G because that is our given Lie algebra. In the example that we'll work out, our given Lie algebra is Witt. And what we want to sort out is what the bracket is on this new Lie algebra that we're constructing, G prime. In our example over here, that is the Virasoro algebra. Okay, so that's important to keep straight right now. Okay, so let's get rid of this and then we'll move on to the next step. Okay, so let's reiterate what we had on the last board. We had this short exact sequences of Lie algebras, an abelian Lie algebra here, our starting Lie algebra here, and the one that we're constructing by fusing these two things together. And this G prime may not be unique. A priori, there may be many, many, many different ways of appropriately fusing G and A together. As we'll see down here in the case of Virasoro, there's only one way. In other words, the extension is unique. And since this is the example we'll be playing with, that'll happen for us. But it's most definitely possible that you could centrally extend G by A number of different ways to get a Lie algebra G prime. Okay, so let's also recall that G prime is linearly isomorphic to G direct sum A. Then also, we already have a bracket on G. That's like given to us, like over here with Witt. So maybe just for simplicity, I'll call that the bracket underscore 0 because that's the one we're starting with. So that goes from G tensor G to G. So it's a linear map from G tensor G to G or a bilinear map from G cross G to G. Now, like I said before, we want to use this to build a new bracket which goes from G prime tensor G prime to G prime, so that we have this thing still works where these are our kind of given vector or Lie algebra homomorphisms. Now we're going to simplify to a special case. This may seem like a little bit of a cop-out, but this is like a standard thing to do right now, is to look at this special case where A is one-dimensional. So let's just say A is one-dimensional, which means we can write it as the complex numbers with maybe a basis vector, which I'll call C. You could just say the complex numbers here, but it will be useful to have a name for the basis vector of this thing right here. And a lot of central extensions of Lie algebras that are very important are one-dimensional central extensions, like affine Cax-Moody Lie algebras or other things like that. If you want to see some videos on that stuff, let me know. Okay, so we're looking at this special case when A is just one-dimensional. So in other words, we have G prime is isomorphic to G, direct sum this one-dimensional thing. So that means it's mostly G, but you just have this extra one-dimensional thing. Now, before we start building this bracket, I want to make one more note, and that is this vector C, which is the basis vector for A, our one-dimensional thing that we're building the central extension of, is most definitely in the center of G prime. So why is it in the center of G prime? Well, that's because it comes from an abelian Lie algebra, and it is injected into this other Lie algebra via an abelian Lie algebra. And then the exactness sort of forces it to be in the center. Okay, so that's really important. That also means when we start constructing our bracket, we don't need to look at vectors like this defined on our bracket because those will be in the center again. Okay, so we only will have to look at vectors from here and here with our new bracket. Okay, so now let's take, I'll call them X and Y in G, but that's a subalgebra of G prime, so we can view them in G prime. And then we want to define bracket XY. But there's only so much that bracket XY can look like. It has to look like bracket XY naught, where this is the bracket inside of G, with the possible addition of something from the new component here of G prime, which in this case is just one-dimensional. So that means it's this plus a multiple of our new vector. And that multiple of our new vector will depend on X and Y. So here I'll write this as fxy times our new vector, where this function f goes from G prime cross G prime to the complex numbers. So that makes it a multiple of this new vector. So that kind of brings up the next really important question, and that is, what rules must f satisfy? Since we have the structure of a Lie algebra, that really restricts the behavior of f. So let's first of all notice that we know that xy must be equal to minus yx because of skew symmetry in the Lie algebra. But that tells us, plugging that up here, that f of xy is equal to negative f of yx. Okay, so that's good to know, again, by skew symmetry. Another thing we know is that the Jacobi identity holds. Recall that the Jacobi identity says that bracket x, bracket yz, plus sort of cyclic permutations of that give us 0. So the next one would be z bracket xy, and then the next one would be y, and then bracket zx. So we know that's equal to 0. That's, in fact, the Jacobi identity. But then this Jacobi identity, along with this way that we're constructing our new bracket out of our old bracket and then this multiple of C, will give us yet another rule that f has to satisfy. This is a good exercise to work through. All you have to do is replace each of these with their definition up here. So in particular, this one down here looks something like this. So it'll be x, y, z, 0. So that's the first part. And then plus f of x, and then bracket y, z of c. So that's that one. And then you get something else for this one, and you get something else for this one. And then a bunch of stuff cancels from the parent or the original Lie algebra because it satisfies the Jacobi identity. And then in the end, you'll have the following equation: f of x and then bracket yz plus f of, let's see, the next one will be z and then bracket xy. And then finally f of y and then bracket zx has to be 0. Okay, so this looks maybe a little squirrely, but let's notice that there are two things being inputted into each of these f's. There's the vector right there, which is x, and then the vector right here, which is y bracket z, or bracket yz, I should say. Okay, nice. So now let's maybe take this equation as well as this equation to the top, and then we'll get to work on constructing our goal algebra. So towards defining the bracket on our extension of our Lie algebra by a one-dimensional vector space, we came up with the following rules for that function f. First, f of xy must be equal to minus f of yx, and then this thing right here, which is related to the Jacobi identity. Okay, and now we're going to restrict ourselves to our example at hand, which is an extension of the Witt algebra by a one-dimensional vector space. And at the moment, I'm saying an extension because we don't know yet that these extensions are unique, but when we do, we'll say the extension and we'll give it a name, namely this Virasoro algebra. And I should point out that this construction is well known and appears lots of places. The place that I found it, which was written very, very clearly, is in A Mathematical Introduction to Conformal Field Theory by M. Schottenloher. So you can actually find this book on his website if you want to check it out. It's broken into chapters, but you can download each chapter. But if you're psyched, maybe purchase it because it helps that person out. Okay, so anyway, this is a really nice readable book if you're kind of at the stage where it's appropriate to read it. Okay, so anyway, let's get to this. So let's apply this rule to basis vectors from Witt. Remember, those look like this, but at the moment, it doesn't matter that they have this form with the derivative. All that matters is that we know the commutator down here. Okay, so let's look at f L0 and then bracket LM LN. So you could do this more generally with like maybe an L something else here if you wanted to, but it's most advantageous to look at these three basis vectors for Witt. So L0, LM, and LN, where M and N are arbitrary vectors. Okay, so let's cycle this through to form this equation. So the next thing will be f of Ln, and then that's bracketed with L0, Lm. And then the next one is f of, let's see, Lm, and then that's going to be, let's see, Ln bracketed with L0. So we know that that is equal to 0, again, by our previous construction. Okay, so now let's apply our commutation relations or our bracket relations to all of these parts in here. So let's see, this one gives us something simple. So we've got m minus n, L of m plus n. So that's easy to see. This gives us 0 minus m, and then L of 0 plus m. I'll just write that as L of m, or Lm. And then finally, this one right here gives us n minus 0, L of n, Ln plus 0, so just Ln. Furthermore, our function f is kind of clearly bilinear, which means we can factor constants out of both parts. That's really built into a previous definition of how we constructed this function. I won't go over that super carefully, but I think it's pretty clear. So that means we can take these constants out. This m minus n, this 0 minus m, and then this n. Okay, so let's see what that will leave us with. So that'll leave us with m minus n, and then we have f of L0. Then this is going to be Lm plus n. And then let's see, this one is going to be a minus m, L of Ln m. Okay, so that's starting to look good. And then finally, this one over here will be a plus n f of lm ln. Okay, cool. And then again, that is equal to 0. Okay, so next up what I want to do is maybe switch these, the ln and the lm, so that they match with this thing over here. We can do that because we've got this skew symmetry of our f. So that means I can change this n to an m and this m to an n, leaving me with lm ln. That just changes the sign right here. Then I can combine these two guys together, so that's pretty nice. That gives me something that looks like m plus n. So m plus n, and then we've got f of lm ln. Okay, nice. And now we can solve for something. So maybe we could solve for lm ln inside of f. So that's going to give us the following. F of lm ln will be equal to, let's see, we'll have n minus m over m plus n, f of L0 lm plus n. So we've got this relationship of this term with that term over there. Notice I switched the sign as I moved it to the other side of the equation. Another thing we have to be careful about is that the denominator here is not 0. So this is in the case that m plus n is not equal to 0. We'll look at the case when m plus n is equal to 0 afterwards. Okay, so now where do we want to go from here? Well, we're going to do a little bit of a trick, but it doesn't change the overall algebra. It just lets us simplify this a little bit. So let's define the following function. So this g goes from Witt to the complex numbers. So in other words, g is in the dual space of Witt. So just recall that the dual space of a vector space is the set of linear transformations from the vector space to the ground field. Okay, and then how is this defined? This is defined so that g of L sub k is equal to 1 over k times f of L0 LK. Okay, and then like I said, this looks like it comes out of nowhere, but it works really nicely. And a lot of these things kind of have tricks. Okay, and then this is only when k is not equal to 0, because clearly we can't divide by 0. And then if k is equal to 0, we have g of L0, which will be defined to be minus half times f of L1 L minus 1. Okay, so let's bring some of this stuff up and then we'll keep going. So far we've done quite a bit. So towards defining our bracket on a central extension of Witt, we have the new bracket is equal to the old bracket plus this function fxy, well, f evaluated at xy times the basis vector for the extension part. Furthermore, in our case, we determined that that function had the following property. F of lm ln was n minus m over m plus n, f of L0 lm plus n. That's obviously when m plus n is not 0. We're looking at that case later. Then we defined this new function, which was in the dual space of Witt, by g of lk is 1 over k f L0 lk, and g of L0 is minus half f L1 L minus 1. And then we can put these two functions together to define a new function, which I'll call f prime. And f prime evaluated at xy is f of xy plus g of the bracket of xy. So notice that g only has a single input. So that's how you make sure that both of these vectors are influencing this input over here. Furthermore, another thing that we're not going to check is that replacing f with f prime in this construction of our bracket produces an isomorphic algebra. And that's just by the way that this g is defined. So because of that, I'll just put a prime up here where this is our f prime. So that's this, that produces, like I said, an isomorphic algebra to having an f there. And now we can just determine what f prime is, which is actually a little bit easier than it is to determine what f is. Okay, nice. So now let's get to it. Let's define f prime of LMLN. So first of all, we know that that is going to be f of LMLN, which is this thing up here, so we can write it using that version. So n minus m over m plus n, f of L0, Lm plus n. And then we have that's plus g of the bracket of LMLN. But let's recall the bracket of LMLN was this thing over here. So that's g of m minus n, and then Lm plus n. But now we know g is linear. Remember, it was in linear transformation from Witt to the ground field. It was in the dual space. So that means we can take the m minus n out, and then we can evaluate g at Lm plus n. We know that m plus n is not 0, so we can use this one right here. That gives us an m plus n in the denominator, and that gives us an f of L0 Lm plus n as an extra term. But now look at what happens here. We have this cancels with this, which is equal to this. So all of those cancel out, and we have this f prime LMLN is equal to 0. That's when m plus n is not equal to 0. So that means the only possibility of getting something new out of the bracket is if this Lm plus n is equal to 0. So let's see. So far, our new bracket takes the following form. We have Lm bracket Ln is equal to the old bracket. Remember, the old bracket looks like this. So m minus n, Lm plus n, plus our function evaluated at LMLN, but that's 0 most of the time. The only time it's not 0 is if m plus n is 0, so we can rewrite that as a new function, h, evaluated at m. It only depends on m now. Delta m plus n 0, and then our new basis vector. So it only depends on m because this term is only non-zero when n is equal to minus m, which means n and m are kind of interlinked here, and we only really have one parameter down here. Okay, so that means that all we need to do now is determine what this h of m function looks like. And that's what we'll do on the next board. So we're almost home free. So in our extension of Witt, we have our new bracket must take the following form. Lm bracket Ln is m minus n Lm plus n, and then some function of m times Kronecker delta m plus n 0. In other words, this is 0 unless m plus n is equal to 0, and then our basis vector for our extended part, which we've called that c. And now we are left to determine what this new function h is. Okay, so let's go for it. Let's first notice that h of 0, well, that's going to be the same thing as h of 0 delta 0, 0. But then using our original f prime function, we can write that as f prime of L0, L0. Then remember, when f prime has the same two inputs, you always get 0. So this gives us 0. Really, that gives us f evaluated at L0, L0, which is 0. And then plus g evaluated the bracket of L0, L0, but that's also 0. So that means that h evaluated at 0 is 0. Okay, so another thing that I'd like to notice is that if we evaluate h at 1, that's the same thing as h of 1 delta, and then let's see, 1 minus 1, 0. But that's going to be the same thing as f prime of L1, L minus 1, if we put it back in terms of our original function. But back in terms even further, that's the same thing as f of L1, L minus 1 plus g of the bracket of L1 with L minus 1. But now let's recall, by the commutation relation over here, we know that this is equal to 2L0. But then if you recall, G evaluated at L0 gave us this minus half f of L1, L minus 1. So combining with the 2, that will cancel this thing out. So more thoroughly, this gives us f of L1, L minus 1 from this term, and then minus an f, or maybe we'll write it like this, plus a 2 times a minus half of f of L1, L minus 1 from this term, but that's clearly equal to 0. So that means we know h of 0 is 0 and h of 1 is 0 as well. And then I'm going to give you guys a little bit of a homework exercise. This is not hard to check, but my homework exercise is to show that h of m equals minus h of minus m. And this is going to be for all natural numbers n. Okay, or m, I should say. So that means if we get the value of h at all the positive integers, we also have the value of h at all of the negative integers. Furthermore, this fact immediately combined with this thing right here tells us that h of minus 1 is also equal to 0. So let's see, our function h has a root at 0, it has a root of 1, and it has a root of minus 1. So that tells us that we should be able to write h of m as m times m minus 1 times m plus 1 times a new function. Maybe we could call that function h prime of m, where that's a new function. Now we have to determine that new function. But in fact, the claim that we will make and then prove is that new function is really just a constant function. In other words, we have h of m is equal to m cubed minus m. So notice that's just the expansion of that m times m minus 1 times m plus 1 times lambda, where lambda is a complex number. And this is actually a free complex number. Regardless of what we choose here, we get an isomorphic algebra, and we can see that just by taking this lambda and maybe absorbing it into this basis vector up here. So this is the claim that we're going to prove that will take us home. We're finally ready to finish this off, and that is by proving that this function h of m, which will finish our bracket for our extension of the Witt algebra, is of the form m cubed minus m times lambda, where lambda is like a free constant, which can be absorbed into C as needed. We'll prove this by induction. Our base case is already done. In fact, we've kind of already done 2 base cases. And those are that h of 0 and h of 1 equals 0. But notice that 0 is of the form 0 cubed minus 0. So we're good to go there. And then we just need to move on to the induction hypothesis. Okay, so our induction hypothesis will be that we have some k, which is bigger than or equal to 1, such that h of k is equal to k cubed minus k times lambda. And then from there, we'll consider the next case. And in order to consider the next case, we need to look at the Jacobi identity included in our H map, which is defined in terms of our F prime map. So in fact, by the Jacobi identity, we know that 0 is equal to F prime evaluated at LK, and then the bracket of L minus K minus 1 with L0, and then plus cyclic permutations of that situation. So that'll be F prime of, let's see, the next one will be L0, and then the bracket of LK with L minus K minus 1. And then finally, the last one will be F of, let's see, L minus K minus 1. And then the bracket of L0 with LK. So there's kind of a lot going on there, but we know what those brackets are, so we should be okay. So I won't explicitly calculate what these brackets are and write it down. I'll just write the next step, which follows, like I said, pretty easily. So this first term right here will give us minus k minus 2. Okay, so we'll have 0 is equal to f prime evaluated at lk, and then the bracket of L minus K minus 1 with L1. And then we'll have cyclic permutations of that. So that'll be plus F prime. So we'll cycle it through. So the next one will be an L1 here, and then the bracket of LK with L minus K minus 1 there. And then finally, the last one will be the bracket of L minus K minus 1 out here. So minus K minus 1, or not the bracket, but that's our first entry. And then we'll have the bracket of L1 with LK. Okay, nice. And now we know the commutation relations for these. So that's actually occurring within the Witt algebra. And so we can just use this rule over here. Let's see what that will leave us with. So this first one will give us minus K minus 2, and then we'll have F prime of LK, and then let's see, this is going to be L minus K. Again, that's from this. And then next we'll have plus 2K plus 1 F prime of L1 with, let's see, that'll be L1. So that's what we get for this next term. And then finally for this last one, we get plus 1 minus K, and then F prime of, let's see, L minus K minus 1, and then L of K plus 1. Okay. Now immediately we can see that this guy is equal to 0 because we have the same two inputs here for our f prime, and remember that was like an alternating function, so that goes to 0. And then next we can notice that these are essentially our definitions for our function h. So this is going to be h evaluated at k. This is going to be h evaluated at k plus 1. Actually, it's not quite h evaluated at k plus 1. What we have to do first is swap these, and that makes it negative h evaluated at k plus 1. But now doing that, we can easily solve, and we'll see that h of k plus 1 is in fact equal to k plus 2 over k minus 1 times h of k. And then it's just fairly simple arithmetic, which I'll let you guys check, to see that we end with k plus 1 cubed minus k plus 1 times lambda, which is exactly what we need in order to finish this induction proof. So in other words, we've got h totally determined. You might say, well, what about the negative values? Recall that the negative values can be built out of the positive values pretty easily by something that we saw earlier. Okay, so now we're officially ready. And another thing is that this complete determination of h means that this central extension is indeed unique. We had no choices for the values of h here, other than that lambda, but then that lambda can be just absorbed within the basis vector of the extension and create the same algebra. Okay, so anyway, let's get rid of this, and then we'll present the final definition of the Virasoro algebra. Okay, so finally we're ready for the official definition of the Virasoro algebra, named for M. Virasoro, a mathematical or theoretical physicist. So, like I said before, it's defined to be the unique central extension of the Witt algebra by a one-dimensional vector space, viewed as an abelian Lie algebra. So it has a nice basis built out of those two parts. So it's the span of these operators Ln, as n goes over all integers, plus, or I should say direct sum with this one-dimensional vector space, which I've given basis vector c. And then our bracket is defined as follows, and we proved that our bracket had to have the following form. So bracket Ln is equal to m minus n Lm plus n, so that's from the original algebra, plus lambda, where that's an arbitrary complex number, m cubed minus m delta m plus n 0 c. So we also know that c is in the center, so that means the bracket of c with x is equal to 0 for all x in Vir. Now you might look at this and say, well, now that lambda is kind of free to be anything. isn't there like maybe a standard choice for the value of that lambda? And in fact, there is. You might think at first that that standard choice should be equal to the number 1, but it's not equal to the number 1. It's in fact equal to the number 1/12. And that seems like kind of a crazy number for this to be the standard choice. So that really brings up this question, why? And this question is going to be answered in depth by a follow-up video. Most definitely put a comment down there if you want to see this follow-up video. And the answer to why 1/12 is because of this very, very famous formula that says negative the quantity 1 plus 2 plus 3 plus ... equals 1/12. So in other words, it's related to the regularization of the Riemann zeta function, which is popularly written as the sum of all natural numbers. And that's a good place to stop.